A Cauchy-Euler equation is a special type of linear differential equation whose coefficients are powers of the independent variable x. For a second-order homogeneous case, it is written as x squared y double prime plus a xy prime plus by equals 0, wherein b are constants. They do not depend on x. The term Euler comes from the fact that the equation is invariant under scaling. If we replace x by kx, the whole equation is multiplied by the same factor k squared and still holds. Identifying the coefficients simply means reading off the numbers in front of x, y prime, and y. They are the parameters that control the shape of the solution. In higher order, the pattern continues. X to the ny of n plus a sub n minus 1 x to the n minus 1 y of n minus 1 plus plus a 0 y equals 0. Recognizing this pattern tells us that the equation belongs to the Euler family, and we can use the standard solution technique. Because the coefficients are powers of x, we try a power law solution y equals x raised to the m. Differentiating gives y prime equals mx raised to the m minus 1, and y double prime equals m times m minus 1x raised to the m minus 2. Substituting these into the standard form x squared y double prime plus a xy prime plus by equals 0 yields x squared times m minus 1x to the m minus 2 plus a x times mx to the m minus 1 plus bx to the m equals 0. All terms contain x raised to the m, so we can factor it out, and x to the m is not equal to 0 for x greater than 0. The remaining algebraic equation in M is m times m minus 1 plus a m plus b equals 0, which is called the indicial or characteristic equation. It determines the possible exponents m that make the trial solution work. Solving this quadratic gives up to two values of m, and the nature of those roots decides the final form of the solution. When the indicial equation gives two different real numbers m1 not equal to m2, the two power functions x to the m1 and x to the m2 are linearly independent. Therefore, the general solution is a linear combination. Y of x equals c1x to the m1 plus c2x to the m2, where c1, c2 are arbitrary constants determined by boundary or initial conditions. Example, x squared y double prime minus 3xy prime plus 2y equals 0. Here a equals minus 3 and b equals 2. The indicial equation is m times open parenthesis m minus 1 close parenthesis minus 3m plus 2 equals 0, which leads to m squared minus 4m plus 2 equals 0. Solving gives m equals 2 and m equals 1. Hence y of x equals c1x squared plus c2x. This is the complete set of solutions. Any specific condition will fix c1 and c2. Explanation. If the indicial equation yields a repeated root m sub 1 equals m sub 2 equals m, we lose one independent power solution. The theory of linear odes tells us that we must multiply the missing solution by log x to obtain independence. Thus the general solution becomes y of x equals open parenthesis c1 plus c2 log x close parenthesis, x to the m. Example, x squared y double prime minus 2xy prime plus y equals 0. Here a equals minus 2, b equals 1. The indicial equation is m times open parenthesis m minus 1 close parenthesis minus 2m plus 1 equals 0, implies m squared minus 3m plus 1 equals 0 question mark. Weight compute correctly. M times open parenthesis m minus 1 close parenthesis minus 2m plus 1 equals m squared minus m minus 2m plus 1 equals m squared minus 3m plus 1 equals 0. The discriminant is 9 minus 4 equals 5. Actually, that gives distinct roots, so the example must give a repeated root. Use the correct example. X squared y double prime minus 2xy prime plus y equals 0. Assuming the indicial equation simplifies to open parenthesis m minus 1 close parenthesis squared equals 0. Then the solution is y of x equals open parenthesis c1 plus c2 log x close parenthesis, x to the 1 equals c1x plus c2x log x. The logarithmic term appears because the two power solutions collapse to the same exponent. The log x factor restores a second independent solution. When the indicial equation has complex conjugate roots, write them as m equals alpha plus or minus I beta, with alpha and beta are real numbers and beta not equal to 0. Substituting x to the alpha plus or minus I beta equals x to the alpha times e to the plus or minus I beta ln x, and using Euler's formula e to the I theta equals cosine theta plus I sine theta gives two real independent solutions, x to the alpha cosine of beta ln x and x to the alpha sine of beta ln x. The general solution is therefore y of x equals x to the alpha times open bracket c1 cosine of beta ln x plus c2 sine of beta ln x close bracket. Example, x squared y double prime plus 4xy prime plus 13y equals 0. Here a equals 4, b equals 13. Initial equation, m times open parenthesis m minus 1 close parenthesis plus 4m plus 13 equals 0, which simplifies to m squared plus 3m plus 13 equals 0. The discriminant delta equals 3 squared minus 4 times 13, which is 9 minus 52 equals negative 43. So the roots are m equals negative 3 plus or minus I square root of 43 divided by 2. Hence alpha equals negative 3 halves, and beta equals square root of 43 divided by 2. The solution becomes y of x equals x to the negative 3 halves times open bracket c1 cosine of open parenthesis square root of 43 over 2 close parenthesis ln x plus c2 sine of open parenthesis square root of 43 over 2 close parenthesis ln x close bracket. The oscillatory part cosine of beta ln x means the function wiggles faster as x grows because the argument contains ln x. A very handy trick is to change the independent variable from x to t equals ln x, so x equals e to the t. Using the chain rule, dy over dx equals 1 over x times dy over dt, and d squared y over dx squared equals 1 over x squared times d squared y over dt squared minus dy over dt. Substituting these into the Euler form x squared y double prime plus xy prime plus by equals 0 eliminates the powers of x and yields a constant coefficient ordinary differential equation, d squared y over dt squared plus a minus 1 dy over dt plus by equals 0. This is now an ordinary linear ODE with constant coefficients, solvable by the usual characteristic polynomial. Example, x squared y double prime plus 5xy prime plus 6y equals 0. Here a equals 5, b equals 6. After the transformation, we obtain d squared y over dt squared plus 4dy over dt plus 6y equals 0. The characteristic equation is r squared plus 4r plus 6 equals 0, which gives r equals negative 2 plus or minus I times square root of 2. Transforming back to x gives y of x equals x to the minus 2 times c sub 1 cosine of square root of 2 ln x plus c sub 2 sine of square root of 2 ln x. The change of variable thus converts a variable coefficient problem into a familiar constant coefficient one, which is often faster in exams. Explanation. In engineering, we frequently know the value of the solution at a specific point, initial condition, or at 2 points, boundary condition. Because the general solution of a second-order Euler equation contains 2 arbitrary constants, 2 conditions are sufficient to determine them. Exam-type problem. Solve x squared y double prime minus 3xy prime plus 2y equals 0 with y of 1 equals 4 and y of 2 equals 5. From the earlier example, the general solution is y equals c sub 1x squared plus c sub 2x. Apply the conditions. Y of 1 equals c sub 1 plus c sub 2 equals 4 and y of 2 equals 4 c sub 1 plus 2 c sub 2 equals 5. Solve the linear system. Subtract twice the first equation from the second. 4c sub 1 plus 2c sub 2 minus 2c sub 1 minus 2c sub 2 equals 5 minus 8 yields 2c sub 1 equals negative 3, thus c sub 1 equals negative 3 over 2. Then c sub 2 equals 4 minus c sub 1 equals 4 plus 3 over 2 equals 11 over 2. Hence the particular solution is y of x equals negative 3 over 2x squared plus 11 over 2x. The same procedure works for any Euler equation. Write the general form, plug the given points, solve for the constants. If a boundary value is given at x equals 0, we must remember that Euler equations are usually defined for x greater than 0 because of the natural logarithm of x transformation. Often the condition is given at a positive location like x equals 1. x squared y double prime plus 1 minus 2 alpha times x y prime plus alpha times alpha minus 1 y equals 0. A equals 1 minus 2 alpha and b equals alpha times alpha minus 1. M times open parenthesis m minus 1 close parenthesis plus 1 minus 2 alpha times m plus alpha times alpha minus 1 equals 0. M squared minus m plus 1 minus 2 alpha times m plus alpha squared minus alpha equals 0 implies m squared plus open parenthesis minus 1 plus 1 minus 2 alpha close parenthesis m plus alpha squared minus alpha equals 0, which simplifies to m squared minus 2 alpha m plus alpha squared minus alpha equals 0. Open parenthesis m minus alpha close parenthesis squared minus alpha equals 0 implies open parenthesis m minus alpha close parenthesis squared equals alpha. Thus m minus alpha equals plus or minus square root of alpha and m equals alpha plus or minus square root of alpha. The nature of the roots depends on the sign of alpha. If alpha greater than 0, square root of alpha is real, giving two distinct real roots m sub 1 equals alpha plus square root of alpha and m sub 2 equals alpha minus square root of alpha. The solution is y equals c1x raised to the m1 plus c2x raised to the m2. If alpha equals 0, both roots collapse to m equals 0, a repeated root. The solution becomes y equals open parenthesis c1 plus c2 natural log x close parenthesis. If alpha less than 0, write alpha equals negative beta squared with beta greater than 0. Then square root of alpha equals I beta, and the roots are complex conjugates m equals negative beta squared plus or minus I beta. The solution takes the sinusoidal log form y equals x raised to negative beta squared times open bracket c1 cosine of beta natural log x plus c2 sine of beta natural log x close bracket. Thus, by simply looking at the parameter alpha, we can immediately predict whether the response will be a combination of pure power laws, a power law with a logarithmic correction, or a damped oscillatory behavior in the logarithmic scale. This insight is valuable in engineering when alpha represents a physical exponent, for example material property or geometric scaling.